you so much for the introduction. So like Patrick said, I'm Simona Ondrčková, and I'll be talking about correcting hierarchical plans. So let's begin. I apologize. Okay, so let's begin. So first, let me start off with a little bit of an introduction what hierarchical planning is. So it's an approach to planning by task decomposition. It's essentially similar to how we think as people. Maybe where we like to split more difficult tasks into easier ones. And so, for example, let's say we have a task like delivering some packages from one place to another. So we might split it into something like loading the package, moving to the destination, and unloading the package. And we continue to split these subtasks into smaller subtasks until we get a task that is no longer decomposable. This we call action, and you can imagine as a sort of simple action that the agent or the robot can take. For example, loading one package. So a plan is a sequence of action that must adhere both to causal dependencies between activities and to the decomposition structure. So it means that the main goal task has to be decomposable into the plan, and causal dependency means that all conditions or preconditions of the action are satisfiable. So here on the right, you can see the example. Now, this work about the correcting of hierarchical plans is actually a sort of extension of a previous work where we created a verifier, and the verifier was inspired by parsing in grammars. And so here, what I wanted to show you is how you would look at the sort of task decomposition through the sort of lens of a grammar. So here you can see like a task T that is decomposed into subtask of T1 to Tk, and then we might have some ordering constraints, C. And these can be ordering, like I said, but it can also be like a precondition constraint or a prevailing constraint. So before condition is something like before you unload, there has to be something in the truck to unload. And a between condition is something that you can say between the subtasks of loading and unloading, the truck has to be filled up with the package that you loaded. It can like kind of fall off in the middle of driving or something like that. So on the right, you can see an example. You can see a task deliver, which decomposes into 4 subtasks: move, load, move, and unload. And then you can see a go task, which decomposes into 2 subtasks of deliver. Now here on the bottom, you can see the decomposition 3 or the decomposition structure of how this actual decomposition would look. So on the top, you can see the go task, and then on the bottom is the actual plan. All right. So let's now talk about a little bit about the plan verification and how does this work. So let me first like define or explain the definition of verification problem. Given an action sequence, is it a valid HTN plan? So first we have to check whether the plan is causally consistent, so whether all the action have satisfied precondition and whether it's a proper structure. So how do we do that? Well, the first thing we do is we calculate all the states. How come we can do that? Well, we're given the initial state, which is what is true before we start our plan. And then we can apply the effects of each action in order to calculate the next state. So we add the positive effects of the action and remove the negative ones, and we get the next state. Then we can verify plan executability. So here what we do is we check the preconditions of each action, and we look at the state immediately preceding the action. So for example, if I want to look whether the preconditions of action A3 are correct, we will simply look at the state S2 because it's right before action A3, and we check whether the preconditions are part of the state. And then we group actions to tasks. So here in this sort of gray frame, you can see the decomposition rules written as if it was a grammar. And then on the right, you can see how we slowly sort of build the task. So what we require in order to build the task is that the right side of the rule is ready. So it means that all the actions or subtasks on the right side of the rule must be already created. So for example, we can start by doing a task T3 because we know that actions A1, A3, and A5 are already ready. So we start with task T3. Then we notice that everything for T4 is ready as well. And the same for T2. Now, in order to create the next task, we need to check that its preconditions are valid. So again, we check the state preceding the task. And we also need to check that all the parameters of the action combine correctly. For example, if that be loading and unloading on the same truck, if that's necessary for the deliver task. And then we can notice once the task T3 and T4 are ready, we can actually create task T4. So we build them together. And finally, we're able to create a task T0, which is the final go task. How do we know that is the final go task? Well, because it decomposes into all actions. So we're actually using a slightly different sort of, I guess, definition of verification, where we're trying to find the go task that decomposes into all actions. You can also be given the go task at the beginning. This is the sort of the more standard definition. And we're currently working on a version of our program that does that. But originally we wanted to be able to find that task instead of it being given. Okay. So now let's finally talk about what you came here for, which is plan correction. So what is our motivation? Why do we care about plan correction? So what we wanted to ask ourselves, where is the bug if the plan is invalid, and what can be done to make the plan valid? Because typical plan validators or plan verifiers, they just tell you that the plan is invalid. They don't really give you like an advice on how to fix it or anything else. So what we wanted to do is we wanted to find out some sort of a solution or advice that we could provide to the user. So what are some correction methods? So the first that comes to mind is action deletion and action addition. And this seems to be all we need. Some of you might say, well, what about action swapping? Well, in order to do an action swap, we just need to delete the actions that we want to swap and then add them in the correct order. What about attribute change? Again, we can just delete the action that we want to change the attribute of, and then we can add back the new one with the right attribute. Now, what we focus here on is just action deletion. In the future, we would obviously like to do action addition as well, and then a combination of both. So how do we define this? Given an action sequence, what is the minimal number of actions to be deleted to obtain a valid plan? All right, so let's start on how do we solve this. So in verification, the first thing was to calculate all states. Now, in correction, we actually can do that. Why can we do that? Well, because the state changes. If you delete an action, the state is going to be different. For example, if you delete the first move action, then the track is no longer going to be at position B for all the following actions. It's going to be at position 8. So obviously that's different. Now we could calculate all the possible states, but that would be like a huge list. So we came up with a different solution. Instead, we create timelines. So what is a timeline? We take atoms, or essentially conditions that are part of the initial state, or actually not just of the initial states, any condition that can happen in the planning process or in the domain that can exist. And we mark which actions support this condition or this atom and which action threatens it. So how does that work? Well, let's look, for example, at this action load 3, this one, load 3 BQ. So the load 3 BQ has an effect that the package is loaded onto the track. So you can see that if you look at this atom loaded Q, you have +3 here. +3 means that this action supports this condition. And then what this does, it takes the package away from where it was, which was on location B. So it actually, so the on BQ, this means that package Q is on location B. It deletes this or threatens this atom. After the action, the atom is no longer through. So we mark this here with a -3. So we do this for all the conditions and all the actions. Every action marks which atom or condition it supports and which it doesn't support. Okay. Now, what do we do with these timelines? Well, we create a support and delete lists for action. So if an action precondition is violated, we need to find a support action and delete all intermediate threats. So let me show you here on the bottom. So this is the same plan as we had before, and the same time on the bottom, you can see the delete and support lists. So let's look again at the load action. And we can see that the preconditions for the load actions are empty and add location. So what this means is that it needs to be empty in order for me to load it. But unfortunately, the previous action load 2 actually threatens this empty atom, this empty condition. So that means that these two actions are incompatible, because if I already loaded, then the track is full and I can't load again. So I will put the load 2, the action 2, into my list of delete actions. I need to delete action 2 in order to be able to use action 3. And then we look at the second precondition, which is that the track needs to be at location, which means that we need to be at location B, which we can see that the first action move satisfies. So we actually say that we need the first action to happen in order for this action load 3 to be valid. So we put it into the support list of actions. And we do the same for every single action. Now, the final step is to build the decomposition structure. So how do we do that? Well, first of all, we need to check the parameters and find out like which subtasks are combined correctly together in order to create this main task deliver. And then what we do is we take the delete lists and we merge them, and then we take the support list and we merge them as well. We create a union. So for the delete lists, we get a delete 5 because we're combining actions 1, 2, 4, and 6. And for the support, we actually get 1, 2, and 4. But from the support list, we then remove any action that is part of the task, because the idea of support is something I need in additional to this task in order for this task to work. But if it's already part of the task, then we know that this action will definitely be in the plan, so we don't need to like additional support to this. So we remove all of those, and then the support is empty. Now, in order for this task to be the goal task, it has to decompose into the most actions, and it cannot have any extra support actions outside of itself, because then it wouldn't be valid. It would need something extra in order to make itself valid. So here we would find out that the goal task is delivered, and we need to remove 2 actions, actions 5, and action 5 in order for the task to be valid, and also action 3 because it's just an extra action that we don't need. Now let me jump to empirical evaluation here. So what we did here is we created a comparison with the plan verifier, because what we wanted to do is we wanted to find out what is the overhead of this plan correction, because if the overhead was huge, then obviously no one would use this, because while it's nice to have the information, if it's so slow, nobody's going to care. So we did a comparison of 4 different domains or types of domains: PCP, transport, kitchen, and satellite. And first we compared it on valid plans, and the overhead is very small, as you can see over here. But then we did also obviously comparison on invalid plans as well, because again, if the overhead is huge, nobody is going to care. So you can see here with the evaluation that actually, if you look at the PCP and transport domains, the overhead is pretty big. Why is that? Well, because the invalidity of the plan is caused by the action causality. So the original plan verifier, it only does the first 2 steps. It calculates the states and checks that the plan is executable, and then it's done. It doesn't need to. It doesn't start building any decomposition structure, as opposed to this correction plan, which obviously needs to build a decomposition structure to tell us what is the task that decomposes into the most actions. So that's where sort of like the difference and the timeline comes from. Now, if you look at the kitchen and satellite domains, you can again see that the overhead is very small. And the reason for that is that the plan invalidity is caused by the actual decomposition structure. There's no task that decomposes into all actions, but the actual actions are valid by themselves. Okay, I'm going to go very quickly over to the conclusion because I believe I'm a little bit over time. So what we did is we proposed the first approach to correct HN plans by action deletion. We were sort of extended our verification method based on parsing, and we made sure that it has a small overhead, assuming that the verification also does all the work to do the decomposition structure. And the next step is action addition, and then a combination of action addition and action deletion. So let me know if you have any questions.